This is for 1 and day 14 from Math 345. We're looking at the numerical approximations of infinite limits. In the first half of this lesson, we talked about in the case when the integrand became infinite at the left endpoint. And so in this case, we're going to expand on that and talk about when the integrand becomes infinite at the right endpoint or at some point in between, or if the limit itself is unbounded. And so we're going to cover the other cases. And the reason why we started with the case when the left endpoint here was unbounded was that we can convert the other cases to this special case when the left endpoint is unbounded. Okay, so let's first consider the case when the right endpoint is unbounded. In this case, we're going to make the change of variables, and we're going to let z equal negative x, and then dz becomes negative dx. So substituting those values in, we get that, and then using the fact that the negative from the z substitution, I kind of like the u substitution, here allows for the change in variables, then we've removed the left endpoint from being, or the right endpoint from being the point of contention, the point where the integrand was infinite, to now becoming a left-hand point problem. And we would proceed in handling this one just like we did in the case first discussed, okay? So this is the first case when the right endpoint becomes unbounded. And so how do you handle that? You make a change of variables, reducing it to the left endpoint, and then proceed as we did in the previous one, okay? Which is what I was summarizing here. So if it's the right one, make the substitution, and then it becomes a left one, okay? The next case is what happens if you have a point in between, right? So what happens if there's an unbounded point at some point C in between A and B? Well, using the property of integrals, we can divide that up into the case of from A to that point C of f of x dx, and then plus C to B. So depending on whatever, what this case is, right? So C is the endpoint of unboundedness. For the integrand, and depending on how that breaks up, it could be a left-handed or a right-handed situation. If it's a left-handed and it's in this situation, then you would just handle it as we did before. If it's a right-handed, then you would handle it just like this. And if it becomes the case that it's still unbounded in both situations, then you would split it up like so. And then this case is just like the case above. And so you would make the same substitution here and convert it then into a situation that looks like this. And then you would have two integrals to compute. This would already be the left-handed situation, and you're converting this one to the left-hand situation. So you would have two left-handed situations in that case, which you would then proceed to handle as we discussed in the first half of this lecture. Okay. All right. And then in the next case is what happens when the limit itself is unbounded. So if we have something of the form where the integrand is dx over x to the p, where p is greater than 1, then we want to convert it to a single left-handed endpoint with a single and converted to a single expression at the left endpoint, or with a single expression with a substitution. So we can do that. That's my shorthand for saying we can make this substitution, which will allow us then to convert it into a case in which we know how to handle it. So let's go ahead and look at that. Let's explore that a little bit. And what would that look like? So if we let t equal x to the negative 1, then dt would equal differentiating, of course, and substituting back in. This is negative 1 over x squared dx, okay? So if we plug those in, as you would expect, just straight substitution, you get a t squared dt and a t to the negative p, or negative t to the p, okay? The limits of integration are from infinity to 1 over a, and then flipping those, we get as 1 over a into 0, and then using properties of exponents, this is dt over 2t to the 2 minus p, okay? Or if it's a function where you're having that issue, then you would just make the substitution. So it's the same exact substitution that you're making. You would just plug in the 1 over t into the function itself, whatever that f may be. Okay, and in either case, then this becomes an unbounded integral at the upper limit there. Okay, so let's look at this a little bit more in the following example and consider what that might look like. So we have this approximation. So we want to approximate the integral from 1 to infinity of x to the negative 3 halves times sine of 1 over x dx. Okay, so we're going to make that substitution. We're going to let t equal x to the negative 1. And if we do that, then the integral becomes from 0 to 1 of t to the negative 1/2 sine of t dt. So now this is of the form. And so just like we did before, we're going to plug in. So our left endpoint is where the integrand is unbounded. So we're going to plug in a Taylor polynomial for P4 using the Simpson composite rule. So first we're going to generate that Taylor polynomial. For sine of t, we're going to expand about 0 in the first values. And so our Taylor polynomial is p to the fourth, or not p to the fourth, but p4 of t is t minus 1/6 t cubed. And again, that's for sine of t about t equals 0. So that's a Taylor polynomial. And then our g of t is going to be then the sine of t minus t. Remember, this is the minus sign here, so these signs switch over t to the 1/2. And this is true between 0 and 1. And we define that g of t is exactly equal to 0 when t is equal to 0. And note that this is in the class of continuous functions of degree 4 on the interval from 0 to 1. Okay, so then we can expand our integrand. From 0 to 1, we have t to the 1/2 minus 1/6 t to the 5/2 plus our g of t, capital G of t, integrand, which is here. Okay, integrating the left-hand side here, or the first integral, we get this value. And then we're going to have to approximate this integrand using the composite Simpson's rule. So we're going to use n equals to 16 here to get a really good approximation, make that interval size small enough. And if we do that, the result of this one comes out to be 0.61904761, and the result of this, using this composite Simpson rule with n equal to 16, turns out to be 0.0014890097. And so adding those together, we get the approximation to be 0.620536661, which by the error bound is accurate to within 4 to the negative 8 degrees. So that's a pretty good estimation then for the actual value of this integrand. Okay, I hope that was helpful. Look forward to seeing you in the next video.